So thank you for coming in such a big number. I would like to talk about debugging binaries. I would like to start with a classic ways so that all of you can remind yourself of the ways you debug C programs. If you don't debug C programs, this will be a little bit quick for you maybe, but you'll see. So how do you debug C programs? I have some ways to do it using tracers and debuggers. How many of you use strace? Sometimes, at least. Thank you very much. So many people. Cool. This is a good starting point. You've seen it. How many of you use ltrace occasionally for tracing library calls? Not so many, but it's still very useful because, for example, getThereIsInfo is a library call that does not have a system call. Yeah. If we go back to strace, the purpose of strace is to see what exactly the application does with the operating system kernel, what system calls it calls. How many of you ever used or at least read more information about system tab? Cool. Someone. System tab is different from the other traces in that it creates custom kernel modules and can trace a lot of stuff that the other tracers cannot, because it's not based on an existing API, but rather resides right in the kernel. You can debug kernel functions with it, you can debug user space. It's very flexible. And how many use GDB? Or maybe also LLDB? Nobody uses LLDB. Okay. Yeah, it might be a bit difficult at times. I tried to use it as well. Cool. So with GDB, you can use commands. You can use commands to do all the debugging. You can use some front ends to GDB to have a GUI debugger. But what I like about GDB is that it is fully scriptable. So you can create a full scripted GDB session like this. In this case, the program starts. The getThereIsInfo function, which I used for the example, even for the strace, the program runs until it reaches the getThereIsInfo function. Then you get the backtrace so that you know where it was called. You can get the variables printed and so on. This is a very simple session. How many uses scripted GDB? How many of you use it? Okay, not many. So this is already something that might be a new helpful thing. I have one more step here. I call it black magic because in this case, during the debugging session, you actually modify the program. And you can combine it with the scripting as well. So for example, this GDB program will go to the first call of getThereIsInfo, and then it will set the name to something else than the program specified. So you can force the program to do something else than the programmer intended. And this is useful for some really corner cases when you cannot reproduce a problem. You can still reproduce a situation in the code that you would otherwise not achieve. In addition to that, both GDB and LLDB are scriptable using Python. I tried using it. It's not so much ready to use. It's not so easy to start with. I think you can see it. Yeah, the data structures are not so easy as you are used to in Python. But what I would like to talk about here is using just pure Python. And in order to use Python for the debugging, the preliminary step is to see what the debugger does. And in this case, I'm using a tracer ptrace for the example, but it doesn't matter. You can do the same with GDB. You can trace what the tracer does, and what we will see are some system calls. In this case, it's a ptrace system call with lots of different options, and those different options let you do the exact same steps that the debugger does. So you can program all of this yourself. This output resembles how you write it in C. You can do it in C, you can do it in any other language. Okay, there's another way to debug. Just think about the code and ask others, and sometimes even just asking others is a solution, even without the answer. You know that. So what you can do here is to program this yourself, and you will need to choose the language. And Python is a good choice, but let's make some assumptions before choosing. Also, in order to be complete here, you might also want to somehow isolate the application from the rest of the system. For example, for debugging networking, you can have visual network interfaces in containers, for example, but the containers are not what we need to use here. We actually need to have automation, we need to have a scalable scripted solution in order to debug repeatedly, to check what the program actually does, and to check many programs for the same features. For example, network client programs, you can check them how they connect to services, and they should normally connect to services the same way by calling the same system calls. You can analyze the results. So in order to do that, we need to have some framework. We don't have one ready to use. There are some options like LNST for some cases, but the problem with LNST, which is Linux Network Stack Test, is that it requires its own network interface for communication, so it actually does not allow you to test network applications in a clean environment. You could use classic container solutions. On the other hand, they don't allow you to easily connect the debugging with the isolation. So finally, what you need to use in order to get debugging, isolation, all of this together, all of this scripted, you need to use some operating system features, like network namespaces in Linux, which are in most cases used using the unshare system call with, again, many different options. And you can do that in C. And you can do that in other programming languages. So the question is whether we want to do everything in C. We are on a Python conference, so most of you already know that we won't, because it's difficult and you have so many problems with C, and you cannot work easily with the data structures and so on. So definitely C is not the best language for this, or otherwise you would not go to Python conferences. You could choose the Unix shell, which is quite a natural choice for low-level system maintenance tasks and stuff like that. But the problem is that the shell usually relies on starting new processes, and not everything can be done there like you can do it in a C program. Yeah, it's a lot of information that I cannot fit here, but shell is simply not flexible enough for that. Because of that, you need a dynamic language like Python. You have all sorts of choices, but Python is already well integrated with C and well integrated with anything on Linux. So that's a pretty easy choice for you. Now, if you can use all those system calls in Python, you can create just a bunch of functions that will do everything for you. You can later look at the slides. I can send it to you, or it will hopefully be somewhere available to see the details, because there's quite some work in managing the details. What do you need to mount, what do you need to unshare, what do you need to do with the file systems, and so on. And there's some code in Python that you may need, including some boilerplate, like encoding strings between Unicode and UTF. And you also need to have the basic functions available, like the system calls. So here you see something which looks like a mixture of C code and Python. It's the simplest way that I found to use library functions in Python. You could also use system calls almost directly, because there's a syscall function in the standard library. But this is good enough. And this way you can have all available. You can use some boilerplate to check the status, because when you're working with C, you have lots of boilerplate code. When you are working with Python and use the basic C primitives and basic system calls, you need to have all the code as well. So this stuff will look a little bit long, but in the end, the result can look somewhat like this. So for example, this code for mounting overlays, this will allow you to get a virtual file system that will use a read-only base file system that you use for getting all set up. And on top of that, you will use a temporary file system that will hold all your changes. And because you're debugging and testing, you will then abandon all the changes, and you will drop them, and you will start new tests with a clean environment. And this is very fast on Linux. This is very easy. Once you have the basic functions all set up, it's as easy as the code that you see here. I'm deliberately not showing the rest of the code now, because together it looks difficult. But here you see that actually, in the end, this is pretty easy. You can use all this together with mounting the TMPFS, mounting the overlays, setting up the network. It's somewhere here. There's already a Python module for setting up the network in Linux, including all the namespaces. So this is not that difficult. You can even set up a pair of client and server namespaces, so that the client program that you test, you can test it against a server program. Both of them have just the network you need for the test, and all is clean and not very not polluted by any other configuration. And in the end, you want to get back to the debugging, so that in the namespaces, in the operating system, with all the tools that you have, you still want to do the tracing and debugging. There is a debugger that is called Python ptrace. It's created by Victor Stinner. He's still somewhat maintaining it. It works. And you can use that to basically trace all the system calls. That's the very basic way to use it. You can do anything with Python ptrace that you can do with any debugger. It might be sometimes more difficult, but you can drive all the code with your Python program. So in this case, you have the full control, which makes it more easy for full automation. Like if you want to test like 100 applications and their behavior, it's much easier to script all of that in Python. I have here a couple of links that you might want to use. The first one is the container debug example that I created some time ago exactly for a talk like this. There is the full example that you can use with all the details and then all the boilerplate, so it's immediately ready to use. There is a third link, which is from David Bečvářík. There's a little bit more complex implementation of the same thing by another person separately. There's Python ptrace my little framework for testing networking applications that uses all of those concepts already. So you can examine code under the last link that already does all that. So that's the whole presentation, and I would like to know if you have any questions.
We do have a lot of time for the questions, so feel free to ask a very complex one.
Hello. I would like to ask about some examples of applications you had to debug, like you've been dealing with. Mm-hmm. So which kind of justifies use of all this, like mocking the networking interfaces and file systems.
Let me find this one. So this is the framework that actually led me to this whole idea. It has a bunch of test cases. In the test cases, you can combine client and server software in all sorts of ways. There's even the as simple program as ping. And the ping client here is represented by a simple script. Not unexpected. And the whole purpose of this framework was to test how the applications handle the networking. One of the purposes here is to check IPv6 readiness of the applications, because there are certain ways the applications must behave in order to be working correctly on IPv6. And not only, the project does not only test the Boolean status of whether the application supports IPv6 or not, but it actually tests IPv4 and IPv6 in quite some details. In this case, if you look at the test cases, this is all client and server software. So you can imagine that any of the programs, or any of the pairs of the programs actually, because this is the pairs of client and server, any of them is expected to connect to the other end in a certain way. And you can examine all of them and analyze them as one bunch of applications that are expected to behave in the same way. It's sometimes not so easy to achieve. There's an example with Python also. And the Python client is just a simple socket client that sends some data over the network. So this is very easy. With some of the software, I had to tweak the test cases so that the software behaves in a specific way, especially for the server side. And all of this can be run by, I will see, sorry, by the main test driver. And I think most of the code is here in the test suite. As an example, here you have a property of the program that we want to check for, and it's how parallel connection works, whether the program even connects to both protocols in parallel. So for example, most browsers do it, but most console software like Corel or wget don't do that and try connecting in sequence. So this is, I think, in basic words, a sample application, sample test driver that can make use of the scripted solution. Thank you for the question. Is there any other question?
This is just tangentially related, and if I have an application which runs already in Docker, I mean, I have a Docker image, but it's just a bare bones one. Do you have any tips how to debug the program which runs in an image where there is no strace, there is no Python inside, and so on? How do I break into the image?
May I ask to repeat the main point of it?
Yeah. If I already have an application which is containerized.
Containerized, okay.
Yes, and I just download a Docker image, and it's based from scratch or from a very, very bare bones distribution. So there are no debugging tools inside of the image. How can I use the debugging tools from my host system to debug the application inside of the container? Would you have any tips on that?
Yeah, it's a very advanced question, so I'm not sure if I can answer right away, but I'd like to discuss it later. Normally, I would like to have the debugging tools in the container, normally. But if I don't have them, it's still a process in the system, so it still should be possible, unless there's some measures that prevent me from doing it. So we might discuss it later and maybe try out something in the evening.
Thank you very much.
Thank you. I guess we still have time for questions?
Yep.
Cool. If you don't have any specific, okay, let's do it.
So when you were talking about containerization, can you just go through your workflow a little bit, how you would use Docker Compose Up, and just a high level overview of how you handle the orchestration of your containers? Not like Kubernetes or anything like that. I'm just kind of looking for a high overview of it.
I'm not sure I understood the question. I'm sorry for that.
So say if you're going through this debugging process and you want to set up a network of containers to mimic, what would your workflow normally look like to set that up? Would you use Docker, then Compose Up, and?
In my case, I do not use any Redis solutions because it's easiest for me to just start namespaces. Basically, the whole idea comes from this test suite, which needs to really have full control over the processes. So in this case, I don't work with any container solution, but basically I'm using the same operating system features that the containers would use.
Any more questions?
If we still have enough time,
Have about 7 minutes.
yeah, then I think we can just for a while look at the code. I think it was container debug example. Because the code for the test suite was a little bit difficult because it does many things at the same time. I'll just look at it. Yeah, that's it. But the code for the example, in my opinion, this is quite understandable because what we do here is just import from the C library all the functions that we may need, like unshare, mount, unmount, in this case umount2, but that's for unmounting, and pivot root. By the way, who knows what pivot root does? The system call. Okay. So what pivot root does is it exchanges your root file system path with some path in the file system, and that's part of the containerization. So if you run pivot root, you have just change root it, like in the classic way, change the root file system to another place, but at the same time, the original file system is still available. So it's like better change root that you can use for containerization and for all of those neat tricks. Who uses FFI in Python? Cool. Who uses some other solution? What is it? Swig, Cython, okay, cool. I've seen some good talks at other conferences in Czech Republic about those. I think it was the PyData meetup or something in Prague. So we can ask those people about more information. Anyway, if you look at the code, we just use some very simple combination of the calls and some transformations, like the encoding for TF8. And so this is the boilerplate. If you skip it, this is the useful part. Like just mounting TMPFS, just mounting the overlay, and you can combine them together with the pivot root. And now you can, this is already somewhat that you can call the program code, because it uses a specific temporary directory that we use for the container. We use the overlays here. And you can later look. It's all online, so just check it out. I can imagine that in the 2 minutes here, you won't understand all the code, but if you take time, it's pretty easy to see what happens here. Yeah. And with this program, the containers.py, you can just start a new process, which runs exactly what you ask for, and you run it in the environment that I specified here, with the overlay, with the TMPFS, and with the network namespace. So I think this is all from me. Thank you for listening, and I'll give the word to others.